Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of free velocity. As usual, before we enter the study of today's lecture, let me give you a quick overview or review about the answer to these four common questions. Question number one, why to study this course? Question number two, how to study this course? Question number three, what are you going to learn from this course? Question number four, how to learn the knowledge from this course. Let me begin with the overview or review to the answer to this first question, which is about the why to study this course. By now, you should know that our mission on Earth include number one, to understand the world. Number two, to improve the world. Then how to understand the world? The answer is to discover the knowledge about the physical world. Then how to discover the knowledge about the physical world? The answer is to make use of sensory data. Then how to obtain sensory data? The answer is to have a measurement and the sensing system. All right. Then how to improve the world? The answer is to invent smart products, smart machine, and the smart system. Then how to invent smart products, smart machine, and the smart system? The answer is to incorporate closed loop feedback control loop inside the design of this machine, this product, and this system. Then what is a closed loop control system? The answer is it is a system with three basic building blocks. One of them is a sensor. So therefore, measurement and the sensing system is extremely important for our mission of knowledge discovery and also for our mission of inventing smart products, smart machine, and the smart system. For example, this slide shows you about the future city scenario in which you will see the presence of smart parking system, smart street lighting system, smart building system, smart home system, smart environmental system, smart healthcare system, and also the presence of Internet of Things. And inside the Internet of Things, there are two basic devices. One of them is a sensor. All right. The second question that you may have in mind is about how to study this course. My advice to you is to put yourself into the mindset of a designer. Then with the keyword of a design or designer, automatically you will ask yourself about these four questions. Question number one, who are the user? Question number two, what are the needs from this user? Question number three, what should be the functionality of a system or product that you are going to develop in order to meet the need of this user? Question number four, what should be the solution behind the design of your future product or future system in terms of sensor or measurement and the sensing system? This could be Internet of a Sensor or Internet of a Things, right? So the answer to question number one is obvious to you because this user include human being, smart product, smart machine, and the smart system. And the answer to the question number two is also obvious to you because all these users have the common need, which is to have sensory data. Then answer to question number three depends on the nature of a user. For example, the smart vehicle may need a certain type of sensor, and the smart robot may need another type of a sensor, right? So the answer to question number three depends on the nature of a user. Then answer to question number four is to study this course. At the end of the study of this course, you will know the solution behind the design of measurement and the sensing system, right? Then the next question is about what are you going to learn from this course. Basically, this course will cover the study of a physical principle behind the design of a popular sensor in electric domain, in mechanic domain, in environmental system, and also in intelligent system. In addition, this course will cover the basic detail about the physical world, the basic detail about the conceptual world, and also you will be able to learn the basic knowledge for you to cope with the randomness in the physical world, and also for you to understand the fascination in the conceptual world. All right. Then the fourth question that you may have in mind is about how to apply learn the knowledge from this course. Basically, you will apply learn the knowledge from this course to guide the design of your future sensor or your future measurement and the sensing system. And the design of measurement and the sensing system will follow two steps. Step number one, it is to transform the value of a physical quantity on the measurement into readable value. Step number two is to do calibration. After calibration, the output value should be exactly equal to the input value, and the unit measurement assigned to the output should be the same as the unit of a measurement of the physical quantity at the input. For step one, you may face two situations. The first situation corresponds to the case in which it is good enough for you to just make use of a front-end sensing element in order to transform the value of the physical quantity on the measurement into readable value. However, in most cases, you may have to make use of at least two sensing elements in order to transform the value of a physical quantity on the measurement into readable value. All right, so these are the general guidelines for you to follow in order to apply learn the knowledge to design your future product or your future system in terms of a sensor or measurement and the sensing system. All right, so now we are ready to move on to study today's lecture, which is about the measurement of free velocity. All right. And in practice, there are specific scenarios in which we can only obtain the measurement about the free velocity. So therefore, this lecture complements the previous lecture, which is about the measurement of a free flow rate. Right. So let's begin with the study of basic physics behind velocity in general, and basic physics behind fluid velocity in particular, right? And this video will show you another interesting application with a fluid system. Then in this case, we can make use of a fluid system to support transportation, right?
Have you ever thrown a coin or nail into the water and seen it sinking? But how come large ships made of iron and steel do not sink? Though they are loaded with passengers and goods, it sails smoothly in large oceans. How is this possible? Watch this video till the end to know more about it, and also an important technique to improve your swimming skills. The discovery of the scientific principle behind floating of ships dates back to the 3rd century BC. The story behind the discovery goes like this. A Greek man was taking a bath in a bathtub. It triggered something in his brain when the water overflowed while he immersed himself in it. He found the answer to the question to which he was puzzling over for a long time, and started running in the streets shouting Eureka. That man is Archimedes, and the principle he discovered was named after him. When an object is immersed fully or partially in a fluid, it displaces fluid equal to the volume of the submerged portion. Archimedes' principle states that an upward force that is exerted on a body immersed in a fluid, whether fully or partially submerged, is equal to the weight of the fluid that the body displaces. The upward force, which is also called buoyancy force, is essential in floating any object over the water. You might have studied about density in school physics. Density is a measure of mass per volume. Pure water has the density of 1,000 kilograms per meter cube. Normally, objects having density less than that of water floats on it. As materials like oil, wood, plastic, etc. are less dense than water, they easily float over water. But how does a ship made of steel float while the nail or coin made of the same steel sink? Steel has density higher than that of water. But when it is used to construct a ship, the newly formed vessel structure's average density gets reduced because of the air that occupies the inner portion of the vessel compartment. When this ship is in water, two forces act upon it. First one is gravitational force due to the ship's own weight, and another one is upward buoyancy force equal to the weight of water displaced by the ship. When the buoyant force is equal to, or more than that of gravitational force, the ship continues to float. When gravitational force exceeds due to events like inflow of water into the compartment, as happened in the case of the Titanic ship, gravitational force exceeds the buoyant force and the ship starts sinking. Same principle is applied in submarines. In submarines, there is a water compartment which is filled with water. The average density of the body is varied by varying the level of water in this compartment. When the submarine is at the surface of the water, the compartment is empty. Water is pumped into the compartment when the submarine has to dive deep into the water. These submarines used during the First and Second World War played a major role in deciding the winning side. Surface naval ships and cargo ships were easily attacked by these submarines, which couldn't be easily identified by the opponents. Now coming to swimming. Our human body is having density more or less equal to that of water. Hence, the upward force will not be sufficient to keep you afloat. You have to make your body spread as much as possible and inhale air to lower your average density. Otherwise, you can also apply Newton's third law by pushing the water downward by your hands and legs. This action creates an equal amount of force in the upward direction, which keeps you afloat. But if you are swimming in water with high density, like we have in the Dead Sea, you need not worry about all these things. Water is so dense that you can easily float even without a simple effort. Thank you for watching this video.
All right, so this video basically shows you another interesting application with a fluid system that is to support transportation, right? And the next video show you one more interesting application with a fluid system. Then in this case, it is to harvesting, okay, energy from the pressure wave of a fluid system. So in this case, there's a pressure wave in the vertical direction, and then we can transform the pressure wave into kinetic energy of the harvesting device, and then transform or transfer the kinetic energy into electricity. All right, so this is another very interesting application with the use of fluid system, right? And in this case, you understand the important parameter is also velocity. It is not flow rate, right? So therefore, velocity is a very important parameter or very important physical quantity, which is independent from flow rate. So actually, flow rate depends on velocity. And here you will see the presence of a velocity inside mechanic energy, inside electric energy, inside thermal energy, for example. Then you will see that the force times velocity equal to mechanic power, velocity times current equal to electric power, and the temperature times flow of heat or flow rate of heat is equal to the thermal power. Then you see we have a flow of a mass, flow of electron, flow of the heat. These are the manifestation of velocity. So you see velocity is a very important physical quantity, right? So in one of the previous lecture, which is about the measurement of the velocity, we have studied the physical principle behind the design of a measurement and the sensing system for entities velocity. And here entity refers to solid, liquid, and gas, all right? And in that lecture, the main focus is on the measurement of solid or rigid bodies velocity. Then in this lecture, we will focus on the measurement of fluid velocity. And the fluid here means liquid or gas, right? So then we have a full coverage of measurement, okay, about the velocity of entity, and here entity will refer to solid, the liquid, and the gas, right? So by definition, entity's velocity refers to the time rate change of a position vector, right? Then we can, okay, draw the velocity time diagram to understand different type of velocity. Let's say you may have a motion with a constant acceleration. Then in this case, the velocity linearly increase with respect to time. We may have a motion with a constant velocity. Then the velocity profile is a horizontal line. Okay, and we may also have an entity which will undergo constant deceleration, right? Then again, you will see a straight line with a negative gradient, right? So this graph basically is help you to understand a different type of entities motion in terms of the property of velocity, right? Then you may want to know, okay, for the case of liquid or gas, what should be the exact definition of velocity? Then in this case, we must consider a bibeam system. Then it is easier for you to understand. Assume inside the pipe system, we consider one element of fluid. Okay, at the time T1, this element of a fluid is at the location 1. Then at the time T2, then this element of a fluid will pass through a reference point. All right. So then there is a travel distance. Then travel distance divided by the traveling time. That gives us the definition of fluid velocity. All right. In case if we know the time function of the travel distance along the x-axis, then first order derivatives of this time function give us the definition of continuous fluid velocity. All right, so this is very much similar to the definition of velocity for rigid body. All right, and this is background knowledge for you to know, because inside the pipe, due to the visco friction between the fluid and the inner surface of the pipe, then the distribution of fluid velocity inside the pipe is not uniform. Then you will see the velocity at the middle of the pipe is larger than the velocity nearer to the inner surface of the pipe. So this is a typical situation of velocity profile inside a pipe. All right, and then how's about the velocity profile in the open water, let's say open sea water or open river water? All right, so there's only visco friction between the water and the riverbed or seabed, because on top the interface is air. All right, then air will not produce too much visco friction to the water surface. So therefore, more or less, you will see this type of velocity profile. Okay, so when the fluid is closer, okay, to the riverbed or seabed, then the velocity will reduce, okay, due to the higher visco friction. All right, so this is something for you to know. Then besides entity's velocity, there is another velocity, which is the wave's velocity. So actually, every one of us are familiar, okay, with the wave's velocity, because every day we see the light. Light is an electromagnetic wave. Light can travel in space, and you know the speed of light is a very, very large number. All right, so this is a very familiar phenomenon to us, but however, we do not pay much attention to the detail of wave velocity. All right, and here you will see we have pressure wave, okay, acoustic wave basically is a pressure wave. And this is also a typical scenario for us to communicate among ourselves when we speak, when we talk, okay, when we pronounce voice, etc. Actually, our mouth is acoustic wave generator, right? So the sound travel in air, then your ear will capture the sound, right? So we make use of a wave to support our conversational dialogue, right? So one phenomenon about the wave velocity should be quite straightforward to you. Here is to consider one cycle as a rigid body, all right? So in this diagram, so you see, consider this is a rigid body. Then we have a wave source line and the wave observation line, all right? So because for sound wave, it can only travel inside the media. If the space is a vacuum, so there will be no pressure wave. However, for light can travel inside the vacuum, right? So when the media has a zero velocity, then the travel time or travel distance, okay, and the sound wave speed are related by this equation of V is equal to the travel distance divided by time, all right? However, if the media has a velocity, then the wave's velocity relative to the observer is no more equal to the wave's velocity. Then it will be equal to the wave's velocity relative to the source plus the media's velocity. It's like when you walk on the roof of a train. If the train is stationary, then your velocity with respect to the ground is equal to the velocity of yourself with respect to your own local coordinate system. When you walk on the roof of a train and the train also move forward, then if there's observer on the ground, then the observed velocity should be equal to your walking velocity plus the train's velocity, all right? So this property is quite straightforward for you to understand, all right? And only tricky sense is for you to consider one cycle as a rigid body. Then you just say, okay, for this cycle, you will move from the source to reach the wave observer, all right? So then we have a wave's velocity plus the media's velocity, and the sum is equal to the wave's velocity relative to the observer, okay? Because here we talk about the measurement, all right? So observer is important because, okay, observer receive the signal, all right? So therefore, the observer can only measure the velocity relative to observer, right? So this is the first phenomenon, and we will apply this phenomenon to guide the design of sensor for the measurement of freeze velocity, because here we can treat the free air is also a gas. It's a free refer to liquid or gas, and the air is one type of a gas, right? So based on this property, we may want to know how to derive the media's velocity, and the media here refer to the fluid in the context of doing the study with this lecturer. So media here refer to the fluid. So how to know the fluid's velocity if we can measure wave's velocity relative to observer? Okay, the answer is quite straightforward, because normally the wave's velocity relative to the source is a constant. For example, when we use a wave generator, so normally we can control the parameter, right? So its velocity in air, for example, acoustic signal travel in air is more or less 340 meters per second. And acoustic signal when you travel in water is about 1,500 meters per second, right? So we know the wave's velocity relative to the source, right? So it means what? If we can measure wave's velocity relative to observer, then we will be able to know, okay, media's velocity. The media here refer to fluid, okay, in the context of doing study with this lecture. So this phenomena is quite easier for you to understand, okay. There's a second phenomenon. This may cause a little bit of difficulty to some of you. However, it is also quite easier to understand, all right? First, we need to know wave ideal situation could be in ideal situation that we could treat wave as a sine wave. Therefore, we can talk about the period. Period corresponds to the traveling time per cycle, okay? Then what is wavelength? Wavelength corresponds to travel distance per cycle, all right? Then 1 over period is equal to frequency. So these are the three parameters which are related to the sine wave, right? So we consider ideal wave, okay? So wave is a sine wave, all right? Then here you always consider this observer there, because here we are talking about the measurement and the sensing system. Observer here means what? Means a sensor or measurement and the sensing system, right? So we just use layman term, observer, okay? So this observer there. So you just consider this situation. So we have a wave source. So actually for one cycle, if you look at the amplitude, so it means what? One cycle consists of a set of amplitude value. If we do the sampling, okay, within one cycle, so you do the sampling, take the amplitude value. So actually we have a series of amplitude value, right? So how to make observer to receive this series of value? So actually you can imagine, okay, we send this value from a wave source one by one, okay? Then observer receive this one by one, then we construct this signal. So this is easier, all right? So they immediately understand this scenario. If listen, there's no relative velocity between observer and wave source, so every value will travel the same amount distance, yes or no? If this is the source is in front of the observer, let's say 100 meters, okay? There's no relative velocity. And the source will send out the sequence of amplitude value one by one, or belong to one cycle, one by one. Then all the value will travel the same amount of 100 meters, yes or no? All right? Then what happens if there's a relative velocity? Because the sending out the amplitude value is one by one sequentially, during this process, the source is approaching observer, the sensor. So it means what? The later value will travel lesser distance. It's only the first value will travel 100 meters. Then the second one will travel less than 100 meters. And the third one will even travel less than 100 meters, sure or not? But in the observer side, we do not know whether the source has a movement or not. Then once we receive all these signals, then we reconstruct them. Then situation is like, then it's equivalent that for us, for the observer to see that the wavelength has been shortened. All right, so it's this situation. So this is this phenomenon has been discovered by Austrian physicist Christian Doppler. All right, and later on is verified by many other scientists. Okay, so this is a very, very interesting discovery. Okay, so actually, if you think in this way, it should be easier. Okay, so you have a source, you have a sensor. All right, the source just send out the sequence of amplitude value one by one. Okay, if there's no relative motion, all the points will travel the same amount of distance. All right, within one cycle. All right, so if there's a relative distance, there's an approach, the source approach the observer, or observer approach the source, whatever relative velocity, then the receive the sequence of a point will have a shorter wavelength. Okay, shorter distance per cycle, all right? Because wavelength means what? Distance per cycle, all right? And when the relative velocity increase, then at the sensor side is equivalent, you will receive a series of amplitude value with longer wavelengths, right? Then from this formula, wavelength equal to velocity divided by f. This velocity is the velocity of this vibration with respect to the source, because this velocity is unchanged. It's easier to understand that you see the traveling velocity in the vertical direction will not be affected by the motion in the horizontal direction. The motion in the vertical direction is not affected by motion in the horizontal direction. So you will see the wave will complete one cycle, regardless of what is the relative velocity between source and observer. It's easier to know. So it means V is a constant. When lambda increase, F will reduce. When lambda increase, then F will reduce. So this is a very interesting phenomenon. Then we can make use this phenomenon to guide the design of a velocity sensor, right? So this is the second property of wave velocity when it travels inside a media. And if between the media and the observer there is relative velocity, then this effect will come out, all right? So this is a very interesting discovery and a very useful discovery, okay? And this video will show you more detail, all right?
Was first described in 1842 by Austrian physicist Christian Doppler. Today it is used in astronomical measurements, in Mossbauer effect studies, in radar, in modern navigation, in studying the motion of stars, and to search for double stars. It is also an integral part of modern theories of the universe. But what is it exactly? Perhaps it is best explained by an example. Imagine a bug in a pool of water. Every time the bug moves its arms and legs, it makes waves in the water. If it moves its legs and arms once every second, an observer standing a few feet away would see a wave come toward them every second. If the bug remains in the same spot and does not move, observers all around the puddle would also see waves coming toward them every second. But what if the bug were to start moving toward the right while still making movements with its arms and legs at the same frequency of once every second? Then, to an observer standing to the right of the puddle, the incoming waves would appear to be at a faster frequency than the waves approaching an observer standing to the left of the puddle. This is because the observer to the right is closer to the bug, and therefore the waves, than the observer to the left. This, in essence, describes the Doppler effect. Another way to explain it is with the example of an oncoming ambulance. When an ambulance approaches you, its siren has a higher pitch as it is approaching than when it is moving away. This is also because of the Doppler effect. It might seem simple and self-evident, but it is an important concept. In 1845, Dutch chemist and meteorologist Buys Ballot tested the hypothesis using sound waves. He found that a sound's pitch was higher than the emitted frequency when the sound source approached an observer, and lower than the emitted frequency when the sound source moved further away from the observer. This happens because the sound waves compress as they approach the observer. This increases the frequency of the wave, and the pitch rises. As the waves recede, the observer will hear a lower pitched noise because the sound waves stretch out. This decreases the frequency of the wave, and the pitch falls. Meanwhile, French physicist Hippolyte Fizeau also stumbled independently on the same phenomenon in 1848. This has led to the French referring to the Doppler effect as the effet Doppler-Fizeau. Finally, also in 1848, Scottish civil engineer, naval architect, and shipbuilder John Scott Russell made an experimental study of the Doppler effect that proved Doppler's theory. Today, the Doppler effect even has applications in robotics. It is used in dynamic real-time path planning to help in the movement of robots, such as in robo-soccer. It can also be used in some types of radar to measure the velocity of detected objects, and in echocardiograms to generate an assessment of the speed and direction of blood flow. But where the theory finds perhaps its most prominent use is in astronomy. The Doppler effect is used to calculate the speed at which planets, stars, and galaxies are approaching or receding from us. It even helps us find and study new alien worlds. It seems the Doppler effect is a versatile concept indeed, with many useful applications.
Right, so this explain to you in detail about this phenomenon. Okay, when there is a relative velocity between the wave source and the wave observer. Right, then actually based on this application, we discover that our universe is expanding. Expanding means the planet are receding from the Earth. When they are receding from the Earth, so it means the wavelengths increase. When wavelengths increase, then the light shift toward the red light. Okay, because the red light has a longer wavelength than the blue light. Okay, so when the color shift toward the red color, red side. Okay, then the frequency will reduce. All right, so based on this observation, then we can make a conclusion about the expansion of the universe. Right, and then based on this observation, then what should be the equation behind the Doppler effect? So actually, the equation is quite simple. All right, so so you remember the wave, okay, with respect to the source has a constant velocity. Okay, so it travel, okay, at a constant velocity. It's only when the source has a relative velocity with respect to the observer, then this relative velocity will increase or reduce wavelengths or increase or reduce frequency. All right, then how it works, basically we just look at the single cycle. So within one cycle, because then it's easier for you to understand, the wavelength is travel distance per cycle. Then within one cycle, the cycle time is t. What should be the relative velocity between the source and the observer? If the velocity is 0, then during time t, the distance increase or reduce is 0. But when this velocity is not equal to 0, then this relative velocity times t is equal to the increase or reduce wavelength, right? So when they move away means what? The relative velocity will increase the distance between source and the observer. Then in this case, the wavelength will increase. When the source move closer to the observer or observer move closer to the source, then the wavelength will shorten. The amount of reduced distance is equal to the relative velocity times the time of one cycle, right? So you get this formula. Then what is t? T is equal to wavelength divided by velocity of the wave itself. Because when the wave travel, nothing change, okay? Within the wave itself with respect to the source, okay? It's only because the media, always the relative motion between the observer and the source, all right? Then the sensor will receive data earlier or later. It's because of this, okay? When you approach, that means suppose every point will travel same amount of distance before the observer will receive them. If there's a relative velocity, then some point will travel less distance, okay? Will reach the observer earlier or later, all right? So then t is equal to lambda divided by v. Now, then what should be the perceived frequency? Perceived frequency should be equal to the velocity of the wave divided divided by the perceived wavelength, okay, received by the observer. So velocity divided by the wavelength, then replace lambda1 by this expression, this result, then you will get this result. So when the source receding or move away from the observer, then for the second scenario, okay, velocity time, divided by lambda2. Lambda2 is the wavelength when the source move toward the observer, okay? Then we get this formula, right? So when the source approach observer, so then you will see in this case, this factor is greater than 1, this factor is smaller than 1, all right? So it's quite simple mathematical equation, all right? So this slide help you to understand, okay, the mathematics behind the Doppler effect, all right? And in practice, as explained inside the video, we can apply Doppler effect in robotics. For example, mobile vehicle or smart car. Today's car all have the new car. All the new car have radar, okay, in front of the vehicle. The radar is to measure the distance, all right? So when the car moves, radar basically will emit a wave channel, all right? So we can direct the radar to hit to get the angle from stationary object. Then in this way, we should be able to measure the relative velocity between our car and the stationary object or a moving target in front of us. All right. So this is the way to estimate the relative velocity between our vehicle and the vehicle in front or something like that. Okay. So then in robotics, okay, we usually robot has a proximity system, and the proximity system consists of ultrasonic sensor. The ultrasonic sensor basically is a wave source channel, okay, because it emits pressure wave into the space. Then we can apply the Doppler effect to derive certain useful information, right? Then in this case, you will see we may want to know the velocity profile of water in a river or in the sea area, because we use a free system to support transportation, and the free velocity is very important to the captain of the boat or ship, okay, because we can control the boat's velocity. If the current has a certain velocity, then it's important for the captain to know this information. So this is why the velocity profile of water in the river or in the sea area is important. Then you will see we can use a color to highlight the high velocity, low velocity, slow velocity, or fast velocity, or something like that. All right. So then immediately we know, okay, the velocity distribution inside river or inside seawater, something like that. Right. And another application is for the submarine to estimate its own velocity with respect to wave source. For example, here, acoustic beacon means this is the wave source. So we may have an installation of a matrix of a wave source. Okay, then the submarine can identify its relative velocity with respect to the nearby wave source. All right, if the wave source could also emit its own positional information, then this could be a way for the submarine to localize its position channel, right? And also the submarine may also want to know what is the velocity of a water flow, because the water flow, velocity of water flow will shift the submarine away from its stationary position. For example, the submarine want to stay here. If the velocity of water flow is 0, then it's no problem. If there's a high current of water coming in, then the position of a submarine will be shifted away, right? So these are the useful information for the submarine to know, all right? Okay, so that's about the basic physics and the mathematics behind free velocity, and in particular behind this phenomenon of Doppler effect. Doppler effect is due to the presence of free velocity and wave source velocity or wave source relative velocity to the observer, right? So now we are ready to study the way of doing indirect measurement and the way of doing direct measurement. So we start with the possible way of undertaking indirect measurement by doing computation, right? So assume inside the pipe system and this system has reached the steady state, then everything is smooth. Therefore, we can apply the basic equation of continuity in terms of energy or the sum of these three terms, because at any 2 points, the sum of these three terms should be equal, because the sum of these three terms is more or less correspond to energy, because pressure is something like a force. So you can imagine this is a work done by the force, this is a potential energy, this is a kinetic energy. That means there's energy conservation. So it means the level of energy is continuous everywhere inside the fluid system, right? So second equation is about the continuity in volume. There's a reason a section of pipe, assume there's no leakage, there's no top up of fluid inside the pipe. Here we talk about the piping system. We are not talking about the storage tank. Okay, for storage tank, we can top up, we can let the fluid to go out. Okay, so here we talk about the inside the pipe at any section. Okay, so there is a conservation of volumetric flow rate, right? So we have these two equations. Now assume that we observe the fluid system at the same height. Then H1 equal to H2, you cancel out these two terms. Then we have this simplified expression. Okay, so then we substitute V2 by this result, because V2 is equal to A1 divided by A2 times V1. Then we have a relationship between V1 and the difference in pressure, all right? So V1 and the pressure difference, okay? So then we can calculate, okay, V1 as a function of a square root, okay, 2 times the pressure difference divided by this constant, all right? So then we can define K equal to square root 2 divided by this term, okay? Then V become, okay, proportional to the pressure difference, inversely proportional to the density, and in front we have a coefficient, right? So this is the basic equation for us to understand, okay? The equation of velocity as a function of pressure variation, right? Right. So now we are going to go through a few examples. So in order for you to know how to apply this equation, okay? For example, here in the pipe system, we know the pressure at the three locations, point 1, point 2, point 3, okay? At the point 1, point 2, point 3, we know the pressure. And we also know that the diameter ratio between point 2 and the point 1 is 1/2. That means the diameter at the point 1 is 2 times the diameter at the point 2, right? Now we want to know what is the fluid velocity at the point 1, all right? So this should be good enough information for us to calculate the fluid velocity, all right? So we apply this equation. So V1 is proportional to the pressure difference, inversely proportional to the density, and the K coefficient is equal to square root of 2 divided by this one. And the question tells you the diameter, okay, at the point 1 is 2 times diameter at the point 2. Therefore, the area at the point 1 should be 4 times the area at the point 2, right? So then this ratio is equal to 4 raised to the power 2. Now we know everything because the pressure difference between point 1, point 2, we know, density of water, we know, okay? So we put in the value, then we should be able to get this answer. But here you must pay attention of doing conversion from atmospheric pressure to Pascal, right? So this is a coefficient for us to do the conversion, right? So second example, is showing you that we have this pipe system. Then we observe 0.1, 0.2, 0.3. Assume for whatever reason we know partial information at the 0.1, partial information at the 0.2, partial information at the 0.3. Now we want to know, okay, from this related value, what should be the velocity of the fluid at the 0.1, velocity of the fluid at the 0.3, right? So from here, you see, we know the volumetric flow rate, we know the sectional area, then immediately you know, okay, Q1 divided by A1 is equal to V1, all right? So then you get the V1. And here is the same situation. We know Q3, we know A3, then Q3 divided by A3 will give us fluid velocity at the 0.3, okay? So, and the next example, now here we have a fluid supply system which consists of 3 storage tank and 3 pipe, like tank 1, 2, 3, pipe 1, pipe 2, pipe 3, and we have let's say level sensor to measure level, fluid level inside tank 2 and the fluid level inside tank 3, and the sensor tell us that the variation of H1 is 0.15 meter per hour. Variation of H2 is 0.10 meter per hour, right? And the diameter for pipe 1, 2, 3 are known, okay? So is 1.0, 0.5, 0.5, and the sectional area of tank 1, tank 2, tank 3 are 10 meters square, 8 meters square, 8 meters square, all right? So then we want to know what are the free velocity at the pipe 2 and the pipe 3, all right? So you will see this basically means free velocity at the inlet to tank 2 and at the inlet to tank 3, right? So here we just calculate what is the volume variation because the question tells you the level increase or decrease in tank 2, tank 3. So the variation of the level times the sectional area give us the volumetric flow rate, okay? Volumetric flow rate area times the variation in height, okay? So here we must do a conversion, okay? Convert hour to minutes or to second, because 1 hour has 60 minutes, 1 minute has 60 seconds, okay? So do this conversion, then you get this answer. Then once we know the volumetric flow rate, then this one divided by the sectional area, okay? Should be, pay attention that the sectional area is pipe, not the tank, okay? Because we ask you to determine the flow rate, okay, or the velocity inside the pipe, not the velocity, okay, about the increase in level, all right? So then the sectional area should be the pipe 2. Okay, this is section area of a pipe 2. Try not to use this one, otherwise you get a wrong answer already, all right? So then diameter is 0.5, you put in the value, you should be able to get this answer, all right? Then for pipe 3, is the same, okay? So the level increase in tank 3 is this one, okay? Then convert it into second, all right? So then you get this volumetric flow rate, okay? And this must be supplied by this inlet here, okay? Then once we know this one, this is the volumetric flow rate at this inlet, then this volumetric flow rate divided by the sectional area of a pipe 3, okay? It's not A3, it's the sectional area of a pipe 3, all right? Divide by this, then you will get this answer, all right? So this is a way for us to calculate the fluid velocity, all right? And here's one more example. Assume, okay, so we use a Doppler effect sensor, all right, to do the measurement, all right? So transceiver B, we have a transceiver A. Transceiver means this one will emit a signal and also can detect a signal. That means it's dual function, all right? So here, let's say transceiver B will emit acoustic signal, okay? And this acoustic signal has a frequency of 500 Hertz, okay? And the traveling speed in water of acoustic signal is equal to 1,500 meters per second, all right? So the transceiver B emit this signal, right? Then this will travel inside the media, which is the free, and this free has a velocity. Then this velocity will produce a relative velocity between observer and the source, right? So then the calculation from received data shows, because once we capture the time function, we can do Fourier transform. Fourier transform allow us to know what is the frequency of this received sine function. Because this is a sine function, here also receive a sine function of a different frequency. Then we do Fourier transform. Now we show you the result. After Fourier transform, we discover frequency is 510 Hertz. Now we want to know what is freeze velocity. All right. So then we apply this formula, right? So then in this case, so the observed frequency is equal to V divided by V minus the freeze velocity, right? Then times the original velocity. So you put in the value. So actually you should be able to get this answer. All right. Okay, so that's about the indirect measurement by doing computation. And our focus here is to know what should be the physical principle for us to follow in order to guide the design of direct measurement, right? So here, I'm going to show you 3 popular design principles, but in practice, there are many other design principles, right? So these are the 3 basic one for you to follow, okay? So they should be good enough to guide the design of your future product or future system in terms of a sensor or measurement and the sensing system, right? The first one is to make use of the drag force, produced by freeze flow, right? Because the drag force could be converted into resistance by a deformable beam, right? Then resistance could be measured by a Priest circuit, or convert resistance into voltage by using a Priest circuit. And then we can use microcontroller to measure voltage, right? So this is the principle number 1. Principle number 2 is to convert the freeze linear velocity into angular velocity. And the angular velocity will produce digital pulse. Then we can use microcontroller to count the digital pulse, right? So this is the second principle. And the third principle is to make use of this Doppler effect, or the property demonstrated by the wave, when it moves inside media such as a fluid, And here, then we have 2 options. One is to measure traveling time, another is to observe the frequency, right? But anyway, we need to measure the time function of the received voltage, right? And in terms of the concept, it's quite complicated, but in terms of the implementation, it's quite straightforward because we have a wave source, We apply time function of a voltage, then produce a sine function of a wave, When this wave travel, through the fluid and reach the detector, the sensor. So actually the sensor, the piezoelectric material, will directly convert the wave or the pressure wave into time function of a voltage, all right? So actual implementation is quite straightforward. So once we receive a time function of the voltage, then we can determine either the traveling time or do a Fourier transform to determine the received, observed frequency. All right. So these are the 3 popular principles for us to follow. All right. So then how to apply principle 1 in order to design digital measurement of a sensing system for free velocity. Then from here, you will see the principle is to transform free velocity into drag force, right? Then transform drag force into resistance, then transform resistance into voltage. And we know microcontroller is a programmable digital sensor of voltage, right? So then this is the blueprint for you to follow in order to guide the design of your sensor or sensing and the measurement system if you apply principle 1. All right. Then here you may want to know how to convert fluid velocity to drag force. The solution is very simple. So you just use a small disc supported by deformable beam, right? Then you have two scenarios. One is to place it inside the pipe. When there's a flow, then the flow will produce drag force on the disc, and then disc will make the beam to deform. If you place a strain gauge there, then strain gauge will convert the deformation into resistance, right? Then in the case of a submarine, so you can install it, okay, outside the hull of the ship, okay? So when the submarine move, there's a relative velocity between the body or the hull of the ship and the water, okay? Then there's a drag force, okay? Then we can convert the relative flow velocity into drag force, right? Then second question, how to convert drag force into resistance? The answer is what? Use a strain gauge. So this is a very popular solution for us to apply, okay? The next question, how to convert resistance into voltage? By now you know, okay? This is a very popular solution for us to convert variation of resistance into variation of voltage, okay? With the use of a Priest circuit, all right? Quite straightforward. Okay, now come to the application of second principle, okay? If we want to apply second principle, then what should be the blueprint to guide our design of measurement and the sensing system, okay? Then in this case, we need to do conversion between linear velocity and the angular velocity. After that, then we need to convert angular velocity into digital pulse, because here we leverage on this capability of a microcontroller in doing pulse counting, because all the microcontroller can take in digital pulse as an input, right? And inside the microcontroller, we have a counter. We have a hardware counter plus software counter, right? And inside the microcontroller, we have a timer, which are programmable, right? So it is not the issue for us to use microcontroller to do the counting of extended pulse, or we can treat extended pulse as a time window, as a single pulse. Then we have a starting time to do the counting and the stop time to stop the counting. Then we can use internal pulse to serve as a pulse for counting, right? So we use external single pulse to serve as a time window. So there are two scenarios for us to handle, and both scenarios are supported by all microcontrollers, right? So you should not worry. Then your focus is just on the conversion from linear velocity to angular velocity, then angular velocity to digital pulse, all right? Then how to convert first linear velocity into angular velocity? So there are plenty of solutions now, right? So here I just show you three solutions. You can have a turbine placed inside the pipe, okay? When there's a flow and the turbine has a plate, okay? In this direction, then the flow will produce drag force acting on the plate. Then the plate will produce a rotating torque. Then this will rotate. If the plate is magnetized, right? So when it pass through this pickup sensor, so you have a magnetic field and the density, intensity vary. Then in this way you will produce a pulse, all right? Or you use this wheel, okay? So when the flow come in, then this wheel will rotate. Then you have a shaft of rotation. Then you can attach incremental encoder to measure the rotary motion, okay, or rotary velocity, all right? Or you have a gear system like this. When there's a flow come in, then these two gears will rotate, right? Then at the shaft, we can place incremental encoder, right? So there are plenty solution for you to follow, and these are three typical ones, right? So once we convert linear motion into rotary one, then how to convert rotary motion into the pulse signal? Then here you will see if the plate is a magnetic material, a permanent magnet, then when you pass through this sensor, this could be a Hall sensor, for example, right? Then the digital pulse will come out. Then here you will see we produce optical pulse, okay? So when this van rotate, then you will see the photo detector will receive light and will not receive light. Then it's like on, off. So you will output the pulse signal, all right? Then the number of pulse is a function of the number of turn rotated by this van per second, all right? And this rotation velocity is a function of a linear velocity, all right? So another way to produce a rotating wheel is this example. Then assume each T is a permanent magnet, okay? They use a Hall effect sensor, then you should be able to produce a pulse as output. So in practice, it's not the issue, okay? So you have a plenty solution to convert angular velocity into digital pulse, all right? And in the simplest case, okay, if you have a rotating shaft here, you can attach an incremental encoder there. Then the incremental encoder just output the pulse, all right? Okay. Then how about the application of a principle 3 in order to guide the design of a measurement and the sensing system for free velocity? Then in this case, okay, we need to play with free velocity and the waves velocity. Therefore, we need to have a pressure wave signal generator, all right? Then let this pressure wave pass through the free, and then free will do modulation. One is to change its traveling velocity, another is to change the observed frequency channel. So then this modulation, then we have a pressure wave, okay? Then this pressure wave could be converted directly into sine wave of voltage. Then from sine wave of voltage, we can determine either velocity or frequency. Okay, if we do Fourier transform, then output should be the frequency or perceive the frequency. All right, so this is a blueprint for us to follow. Then you may want to know how to generate a pressure wave signal. The good news is to apply piezoelectric material. Piezoelectric material is a very interesting material. If let's say we have a sine wave of voltage, let this voltage apply to the piezoelectric material, then it will vibrate, then produce a pressure wave, okay? And the frequency depends on the parameter of this circuit, all right? So it's not the issue. So this drawing basically highlight to you, okay? If we apply electric signal, then we will produce a periodic wave, all right? So then this is what happening, this animation showing you, okay? So here we have, let's say, sine wave of voltage signal, okay? Sine function of a voltage signal. Then we have a pressure wave coming out, all right? Then, okay, this video basically first explained to you about the implementation in practice.
Stethoscopes can convert sound waves to electrical signals, which enable them to listen, record, and play back sound waves coming from the body. One of the most popular ways used to convert sound signal to electrical signal is using a piezoelectric material. The special property of piezoelectric material is that when external stress is applied across the material, it can generate voltage. Let's take a look at how these materials are able to exhibit this unique property. Consider this structure of a silicon dioxide material, popularly known as quartz crystal. When we take a look at this structure from a specific angle, we see it has a hexagonal shape. The big question is why the piezoelectric material produces an EMF across it when you apply a force. To get the answer for this question, first, we need to understand a concept called electronegativity. Here, the oxygen and silicon atoms share one electron. Due to the smaller size of oxygen atoms, the shared electron is closer to the oxygen's nucleus, so oxygen will exert more force on the electron than silicon. As a result, oxygen is more electronegative than silicon and will have a slight negative charge. This also means the silicon atom will have a slight positive charge. So the oxygen and silicon atom together constitute a dipole. In the quartz crystal, these dipoles are arranged such that the center of charges of the negative and positive atoms coincide. Now what will happen to the center of charge if we apply a compressive force across the molecules? The center of charges do not coincide anymore, and there will be a charge separation. This is called polarization. This also means an electric field will be created between the net positive and negative charges. This leads to generation of a small voltage across it. The quartz structure consists of multiple similar hexagons connected in series, which lack a center of symmetry. So now, if we apply a compressive force across the entire material, the individual charge separations of these hexagons will add up to generate a voltage across the material. Let's replace these charge pairs with small cells. It is clear that if we have more cells in the series or thickness of the material is more will be the net voltage developed. Now, what do you think will happen if a voltage is applied across the material? The special characteristics of piezoelectricity is that it is reversible. If a voltage is applied across the material, the positive and negative charges of the material will experience forces in the opposite directions, and the hexagon will get stretched. Similarly, if the polarity of the voltage is reversed, the hexagon will get compressed. This stress or strain is transferred across the material, resulting in a net compression or expansion of the material. Now, let's study the working of an electronic stethoscope. The electronic stethoscope has a very thin diaphragm connected to the piezoelectric material. When the sound waves hit the diaphragm, it oscillates, making compressions or expansions in the piezoelectric material. This produces voltage across the material proportional to the amount of deflection. The voltage is then transferred to an amplifier and filter circuit to get the desired output. We connect the piezo material to a foam spacer and a steel plate to enhance the vibrations, which in turn results in generating more voltage. Thank you for watching the video.
All right, so that video basically show you the dual usage of a piezoelectric material. We can apply voltage in order to produce a vibration, or we can convert vibration into voltage. All right, so that answers the first question. So we can produce a wave signal generator. Then second question is how to modulate a pressure wave signals parameter. Then the answer is let the wave signal to pass through media, and in this case the media is the fluid on the measurement, right? So then you have a different type of design principle, right? So this is one solution. So you have a transceiver here. So transceiver means is a combination of a transmitter plus receiver. So it can send out the signal and also detect the signal, right? And here you have a transceiver here, and here you only have a single transceiver, right? So there are plenty of solutions. Then if let's say we only focus on the use of this information about the traveling time, then in this scenario, right? So then this emits the signal, then this will detect the arrival of the signal. Then we can calculate the time duration, right? Or in this situation, this one emits the wave, then this one detects the wave, okay? So we know time t1 when the wave has been emitted, and the time t2 when the wave has been received. And then we know theta t, right? Based on theta t, since we know the fixed distance, then we should be able to calculate the observed velocity. Then observed velocity should be equal to the velocity of the wave plus velocity of freeze velocity, right? So then we do a subtraction. Then it is straightforward for us to know the measuring the velocity, right? Then in this case, we must capture the received wave signal in the form of time function of the voltage, okay? Convert the time function of the voltage into digital number or digital signal. Then we do Fourier transform, then to know the frequency, receive the frequency. Then based on the difference between the received frequency and original frequency, then we should be able to calculate, okay, the freeze velocity. So these are the two type of implementation with the use of wave signal, right? So then this video showing you a practical implementation, okay?
The most diverse substances are transported and distributed in piping systems every single day. They can include solvents and chemicals, vegetable oils in the food sector, coolants in primary industry, or petrochemical products. The fluids flowing through pipes often have completely different properties. Therefore, different principles are required for their measurement. One principle is flow measurement based on the differential transit time method using ultrasound. The basic physics of this principle can be traced back to the English physicist and Nobel Prize winner Lord Rayleigh. His book on the theory of sound, published in 1877, describes the propagation of sound waves in solids and gases. Here is how this measurement method works. Inside the ultrasonic flow meter, pairs of sensors are fitted across from each other in the measuring tube. Each sensor can alternately transmit and receive an ultrasonic signal. Simultaneously, the transit times of these signals are measured. The ultrasonic signals are generated with piezoelectric crystals applying a voltage. Conversely, a piezoelectric crystal creates a voltage when an ultrasonic signal impacts the sensor. By increasing the number of sensor pairs, it's possible to accurately detect and mathematically compensate for flow profile distortions over the entire pipe cross-section. When there is no flow, the signal transit times are the same, upstream and downstream. Once the fluid starts to flow in the measuring tube, the ultrasonic signals are accelerated in the direction of the flow and decelerated against the flow. As a result, the ultrasonic signals now have different transit times, less time in the direction of flow and more time against the flow. Therefore, the differential transit time measured by the sensors is directly proportional to the flow velocity in the pipe. Together with the known tube cross-section, the actual flow volume can then be calculated. The greater the flow velocity, the greater the measured time difference between the two ultrasonic signals. For ultrasonic flow measurement, the sensors do not necessarily have to be fitted into the pipe wall. With a clamp-on system, for example, the sensors are fastened directly onto the outside of the pipe. They can be retrofitted at any time without interrupting the process. With clamp-on sensors, the ultrasonic signal is passed directly through the pipe wall and into the fluid. The signal continues through the fluid, is reflected on the opposite pipe wall, and then measured by the second sensor. In this example, with a two-traverse installation, the clamp-on design is unique because flow rates can be measured in very large pipes, up to 4 meters in diameter. This possibility increases the areas of application, for example, in the water and hydroelectric industries. Flexible mounting, process safety, and cost effectiveness are the distinctive advantages of ultrasonic flow measurement.
Right. So besides these three popular principles, there are other principles such as making use of image, okay, to determine the velocity in the image plane, then from velocity in image plane to determine the velocity in fluid, all right? So in one of the future lecture, we will talk about the measurement of a visual signal, right? So you see, we use a laser to illuminate, create this laser plane, all right? Then this laser plane will illuminate the particle inside the fluid. Then we use a camera to capture image of the T1, image of the T2. Then you will see we can be able to estimate the velocity in the image plane. Then from the knowledge about the parameter of the camera, then we should be able to calculate the velocity of the fluid, all right? So here is one more example. Then you will see at the time T1, we capture this image. At the time T2, we capture this image. We superimpose them together. Then you see the image of the particle on the go motion in the image plane. And this velocity is related to the velocity of the flow, okay, the free. Another principle is to make use of Coriolis force, because when the fluid move in a circular path or on the go linear motion coupled with angular motion, then there's a Coriolis force occur, all right? So then we can relate the Coriolis force to the linear velocity, because this one could be under control, okay? We know this angular velocity, and if we know this value, then we should be able to relate this value to velocity on the measurement, all right? So let this video show you
substances are transported
example
and
which
distributed in
apply
pipelines every single day. This may include drinking water, fruit juices, oil and gas, as well as chemicals, acids, or alkalis. The fluids flowing through pipelines often display completely different properties. Consequently, there are different principles for their measurement. One such method is flow measurement based on the Coriolis principle. The French physicist Gaspard Gustave de Coriolis set out the physical basis for this measuring principle over 200 years ago. What is interesting is that the Coriolis principle allows the flow of mass to be directly measured. Let's take a closer look at how this measurement method works. A tube is located inside each Coriolis flow meter. An exciter causes this tube to oscillate constantly. Here in an exaggerated example. If there is no flow, the measuring tube oscillates uniformly. Sensors are located at the inlet and outlet and register this basic oscillation precisely. As soon as the fluid starts to flow in the measuring tube, however, additional twisting is imposed on the oscillation as a result of the liquid's inertia. Now, due to the Coriolis effect, the inlet and outlet sections of the tube oscillate in different directions at the same time. The highly sensitive sensors pick up this change in the tube oscillation in terms of time and space. This is known as the phase shift and is a direct measure of how much liquid or gas is currently flowing through the pipe. The higher the flow velocity, and thus the total flow, the greater the deflection of the oscillating measuring tube. The application of the Coriolis measuring principle doesn't stop here. It can also be used to simultaneously determine the density of the flowing fluid. To do so, the sensors also register the oscillating frequency. In other words, how often the measuring tube moves back and forth in 1 second. From the animation, it's clear that a tube filled with water oscillates more frequently than a tube filled with honey, for example, which has a far higher density. Thus, the oscillating frequency is a direct measure of the fluid's density. Both the density and the flow are determined simultaneously but independently via the tube oscillation. Endres and Hauser has continuously revolutionized.
All right. So there are many other principles for us to follow. Okay. So by now it should be good enough. Okay, with the use of these 3 learned principles, you should be able to come out the design of future measurement and the sensing system for fluid velocity. All right. So after the transformation from value of a physical quantity on the measurement into a readable value, always remember to do calibration. Okay, because the calibration will only allow you to assign as a unit of a measurement to the final value, which is the same as a unit of a measurement on the measurement, all right? And in addition, the output, the ZI, is exactly equal to the input XI after calibration, because we want the relationship between XI, ZI to follow this straight line, which is a 45 degree above the horizontal axis. Then here you may want to know, okay, how to produce reference freeze velocity. So actually you can use this kind of a setup because you know, okay, if we maintain h to be constant, then the flow rate or flow velocity at the outlet should be constant, right? So by changing the value of h, then you should be able to obtain a reference value for xi. Then in this way, you use this setup to calibrate your sensor, all right? So after calibration, then your sensor is ready to be used by end user or to be purchased by buyer. Then however, you need to supply this information to the user of your sensor or to the buyer of your sensor. Therefore, you need to do error analysis. Error analysis means use your new sensor to repeatedly doing measurement. Okay, once you give a reference value at the input, you do a repeated measurement for 100 times, 200 times. Therefore, then you can calculate the mean value, standard deviation, etc. All right. Then you should be able to know what is the systematic error, repeatability error, accuracy, etc. And always remember to do the last experiment in which you increase the input, then you do the measurement, then you reduce the input, you do the measurement, then you compare the reading, whether there's a gap between these two sets of reading or not. If there's no gap, that means there's no hysteresis error. Otherwise, there's a hysteresis error, right? So that's all about today's lecture. So the key takeaway from this lecture is for you to know that besides velocity of an entity, there is a wave's velocity. And when we combine the wave's velocity together with the freeze velocity, then there's an interesting phenomenon which is called Doppler effect. All right. So we can make use of Doppler effect to do indirect measurement or to do direct measurement. All right. And in particular, we have studied 3 popular design methods for you to follow in order to guide the design of your future measurement and the sensing system for freeze velocity. Thank you for your attention. I'm looking forward to seeing you in the study of the next lecture.